Hi, good morning. Welcome back to CS560. So today we will continue talking about the second type of searching algorithms, searching algorithms on the graph, which is depth first search. Okay, so DFS is different from BFS, mainly in the perspective of how it's what the strategy it takes in going through the graph. So the main strategy is that it chooses to search deeper in the graph whenever possible, and it will explore out of the most recently discovered vertex that still has unexplored edges. Okay, so it will not go back to the previous vertex until it has exhaustively explored all of its adjacent vertices. So once all of these edges have been explored, the search will backtrack to explore the edges that was at the previous level. Okay, so it's easy to see the difference, how DFS is different from BFS using this simple example here. So if it's a DFS on the graph, then for example, the vertex 1 is our source vertex. It is where we start. So assume that we go from 1 to 2 in our first step, okay? And then our next step will be from 2 to 4. And then after 4 is also explored, we'll go deeper, follow the adjacent edges of vertex 4, which is 5. Okay, so after 5 explored, there's no more adjacent vertices, adjacent edges that connect to vertex 5. So we will backtrack all the way back to node 1 and to vertex 1, and then explore the other adjacent edges of vertex 1, which is vertex 3. So that's where the blue arrow indicates. Okay, so basically the sequence of vertices being visited in a DFS in this particular example is we go from 1 to 2 to 4 and 5, and then we go to 3. Okay, so you can see there is a deep depth preference, right? We go from 1 to 2 and 2 to 4 and 4 to 5, which is a very deep path. Until this deep path is all finished, then we'll go back to the other branch or the other direction. So that is a simple demo of how DFS works. So compare with BFS, which we have been discussing in the previous lecture. So BFS, the basic principle is that we explore all the vertices that are within a shorter distance before we explore any vertices that is beyond the current range. Okay, so in this case we will explore all the vertices that are one edge away first, and then we discover all the vertices that are 2 edges away. Okay, if we start from 1, then we will explore 2 and 3 first, because 2 and 3 they are within 1 edge distance from vertex 1, and then after they are explored, then we will continue exploring 4 and 5. So that is the basic demo of how BFS works. So in this case of BFS, the sequence of vertices being visited is like 2 and 3 are before 4 and 5. So from this comparison, we can have an idea that DFS is quite a different strategy from BFS, and as the result, the sequence of vertices being visited is different, and the resulting tree is also have a different structure. Okay, so we can have different ways to implement DFS, and one of the most straightforward implementation is to use a recursive technique. Okay, so it's quite a simple. So this simple recursive implementation of DFS doesn't provide the function of recording the distance like what we did in the BFS. We didn't record the parent vertex for each vertex in the graph. So it's a quite simple algorithm, and it's a quite simple implementation. And we will look at the simple implementations of DFS first, and then we will introduce a more sophisticated DFS implementation, which which not only record the parent vertex, the distance from the source, but also the visiting timestamp. So that'll come in a later slide. But we'll look at the very simple implementations first. Okay, so in this recursive implementation of DFS, the procedure takes inputs the graph represented by the G and a source vertex implemented by S, represented by S. So the S is where we start, the vertex that we start. Okay, so in this implementation, we assume that each vertex also has a attribute called visited. So it is a Boolean variable to indicate whether this vertex has been visited or not. Okay, so at the beginning, all the vertex in the graph are initialized to false. All the visited attributes are initialized to false. So at the first line of this code, because S is where we start, so we will immediately change the visited attributes of the source vertex to true, and then for each vertex within the adjacent vertex list of S. So G.adj with index S. So this is a list of adjacent vertices that have edges connected to the source vertex. Okay, so for each adjacent vertex of S, we will check if it has been visited or not. So if it is not visited, then we will call the DFS recursive on that vertex recursively. Okay. So that makes sense, right? So we will check each vertex within its adjacent list, and if that is not visited, then we'll go deep into that vertex. So this recursive call what it will do is to set the visited of V to be true as well, and then check the adjacent vertices of V again to see the neighbors of V, and if there's any unvisited neighbor vertex within V, surrounding V, then we'll choose one and go deep into that neighbor vertex. So this is quite straightforward implementation as a recursive algorithm. Okay, so if we look at this example here, if we use the vertex U as the source vertex and we call DFS recursive on the vertex U, then we can see how the in next slide we'll see how each of the other vertices will be visited. Okay, so there's a typo that I need to fix in the previous slide. So at line 2 of this DFS recursive implementation, there really shouldn't be an indent. So the for loop should start at the same level with the first with the line 1 statements. Okay, so here's just a minor fix. So now let's look at how the results will be, what the results will be like if we run this recursive DFS on source vertex U. Okay, so assume that all the vertices are unvisited, so the Boolean variables are all initially false, and the call of DFS recursive on U will first set the visited variable of U to be true. Okay, and then it will use a for loop to go to iterate over all the adjacent vertices of U, which is V and W. Okay, so the sequence matters, but now let's just take an arbitrary sequence in which we visited vertex V first and we visit W secondly. Okay, and the recursive call on the, because V and W, they are all unvisited at first, so the recursive call, so there will be a recursive call on V first, and this call will set the visited property, the visited attributes of V to be true. Okay, and it will go through all the adjacent vertices of V, which is X and Y in this case. Okay, so let's just assume that X is visited first and then Y is visited secondly. Okay, so in the recursive call on DFS recursive on X, we will do the same thing. We will set the visited attribute of X to be true. And then here we need to pay attention, that's because we also need to explore all the adjacent vertices of X, which include Y. Well, in fact, there's only just Y. So we will call DFS recursive on Y, which will set Y visited to be true. Okay, so now if we return from this level to the upper level, which will be the next call of DFS recursive on Y, so when this call is incurred, at that point, the Y is already visited in the previous call, in the previous step. Okay, so when DFS, so in fact, the DFS of recursive call at this step will not be executed, because the if statement will tell us that the Y dot visited is not false before this recursive call. Okay, and the visits on Y is already happened at this step. Okay, so we will skip this step and then jump into the next recursive call on W. Okay, and this call on W will set the visited attributes of W to be true as well. Okay, but it is not ended here. In theory, technically, we still need to check all the adjacent vertices of W, which is X. But since X is already visited, so there will be no more recursive calls. Okay, so I highlighted the edges sequentially in order of when they are visited, and all the bold edges shows the path that we go along the graph when DFS recursive is called. So we first go through from U to V, from V to X, and then X to Y, and then we go back to U to W. Okay, so this is just a recursive implementation of DFS. And now let's look at an alternative implementation for simple DFS, which is an iterative or non-recursive way of implementation. So to implement non-recursively, we need to use some data structure called stack. Okay, and we will initialize a stack at line 1. So a stack is a first in, last out data structure. It's different from the queue that we use for DFS. Okay, so a queue is that the first element that gets in will popped out, will get DQ'd first. But in the stack, it's the opposite. The elements that get first pushed in will get popped lastly. Okay, so the stack data structure supports push and pop operations. The push will add an element to the stack, and a pop will remove the top elements. Okay, so indicated by this graph here, an empty stack looks like this. So when you push an element into an empty stack, it will go to the bottom of the stack. Okay, and after you push two elements into the stack and then you pop one element, then the elements that get pushed in later will be popped out first. Okay, so in this case, the two will be popped out first before one. Okay, so what basically this algorithm does is to use a while loop, and this while loop doesn't end until the stack is empty. Okay, so we will first push in the source vertex into the stack, and then we will keep pop out vertex from the stack. So after one element or after one vertex is popped out, we will check if that vertex is already visited or not. If not, if it's a new vertex, then we will set its visited to be true, and then for all of its adjacent vertices, we push that adjacent vertex into the stack. Okay, so that's basically how the pseudocode tells us. And in the next slide, we will look at an example of this iterative algorithm runs on the same simple example of graph. So when this DFS iterative procedure is called upon the U vertex in this graph, the vertex U will be pushed into the stack. So this is the first element in the stack, so it lies at the bottom of the stack. Okay, so next we'll enter the while loop, and this while loop will not terminate until it's empty. It's totally empty. So within the body of this while loop, the elements we will conduct a pop operation. So the vertex U will be popped out. Okay, after it's popped out, because it's not visited at the beginning, so the if statement satisfied, and we will need to, the line 6 will set the visited attribute to true, and then for all the adjacent vertices of U, which is V and W, they will be pushed into the stack. Okay, so U will be painted gray, which means it is visited now, and then the V and W will be pushed into the stack. Okay, so the sequence matters, but as a demonstration, we just randomly choose that we push in V first and W secondly. So V will be pushed in first, and then W will push in afterwards. So now the stack has two elements in it. So the while loop will continue because it is not empty. Okay, so the next iteration of the while loop will get W vertex popped out because W is on top of V, so it gets popped out first. So after W is popped out, V is left in the vertex, and since W is not visited, we will need to set the visited property, the visited attribute, to true, which means we paint its visited. Okay, and this bold edge means that how we go through the graph is from U to W. We go through, so this edge is visited within this DFS iterative procedure. Okay, So, and then we do the same thing. After W is popped out, we need to check its adjacent vertices and pushing all the adjacent vertices. And X is the only adjacent vertex of W, so X will be pushed into the S. So now within the stack, X is on top of V. Okay, and we enter the next iteration of the while loop. Okay, so next X got popped out, and X is set to visited. It's painted gray, and then all of the adjacent vertices of X, which are V and Y, will be pushed in. Okay, assume that we push in V first and then Y secondly. Okay, so now Y is on top of V and V is top on another V. So assume that we can push in the same vertex repeatedly. Okay, so even though V is already in the stack, we can push in it again to the stack. Okay, so now into the next iteration, Y will be the element to be popped out. Okay, so Y got popped out and Y is painted to gray. Okay, and we'll need to push in all the adjacent vertices of Y. But in this case, Y doesn't connect out to any other vertices. Well, it is connected from V to Y, but there's no edge leaving Y to the other vertices. So the adjacent vertex list of Y is empty. So there's no new vertex to be pushed in at this step. Okay, so nothing will be pushed in. So the iteration of the while loop continues. We will need to keep pop out elements from the stack. So the V will be the next one to be popped out. So after V is popped out, since this is the first time V is visited, we will need to paint it gray. Okay, and but the algorithm goes on, because according to the algorithm, we need to push in all the adjacent vertices of V to the stack. So in this case, the adjacent vertices of V is X and Y, even though they are already visited. But the algorithm doesn't know at this step. It will keep pushing X and Y into the stack. Okay, and we'll go to the next iteration of the while loop. So in the next iteration, while will be got popped out. Okay, but since after it's popped out, the if statement will check if it's visited or not. So after Y is popped out, the if statement will tell us that Y is already visited. So there's no need to push in all the adjacent vertices of Y. There's no such a need. So Y will got directly popped out, and in the next iteration, X also got popped out, and the next iteration V got popped out. So after V is completely popped out, the stack is now completely empty, and there will be no more vertices got pushed in. So after V is popped out, after the stack is empty, the whole procedure will terminate. And now we will have the complete result of running DFS iterative on the simple graph here. So on top of the simple DFS recursive or DFS iterative procedures we have implemented so far, we can go through, or we can search the graph with the strategy of depth first. Okay, so in order to obtain a resulting DFS tree, like what we did in the BFS, we need to modify the pseudocode a little bit to record the parent vertex information for each vertex along the way of the search. Okay, so it's just a simple modification. So in the case of the recursive DFS, we just add one line of code at line 4 to so to assign S to be the parent node of V, and V is within the adjacent vertex list of S. Okay, so right before we visit the vertex V, we will set its parent to be the S, where we go from the previous step. Okay, so with this code, with this modified DFS recursive, we're able to obtain a DFS tree after the procedure is run. Okay, so as a result, we will have a tree available. So this bold edge indicates the parents relationship among these vertices. So after DFS is done on this graph, and if we imagine that if we lift all the vertices by holding the vertex U and lift it up, it'll be a tree like this. Okay, so at the first level, it'll be the children vertex for U, which is W and V, and all the other edges pointed all the way down to from V to X, X to Y. So this is a so-called DFS tree after this DFS is done on the graph. And similarly, we can modify DFS-ITERATIVE also to record the parents for each vertex. So I didn't show the code here, and but as a result, well, we already know that if we follow the steps of the previous DFS-ITERATIVE implementation, the tree will be like this. After U is lifted up, it'll be from the root node will be U and pointed to V to W, and W has one branch pointed to X, and X has two branches from V to V and to Y. So it'll be a DFS tree like this. So it's a different shape. The tree could be different depending on the algorithm, depending on the rules that the algorithm takes in terms of the order of which vertex got visited before which. So that is the results of obtaining a DFS tree upon the graph. So this is the ideal case in which all the vertices are reachable from the source. Okay, so whether it's iterative implementation or recursive implementation, starting from the vertex U, we can always reach all the other vertices in the graph. Okay, but it is not necessarily the case. If we start, for example, from the vertex W, then W is, so imagine W is our source vertex, then the vertex U is never reachable from W, okay, because the edges only goes out from U to the other vertex, but there's no edge from other vertex to U. So if we start from W, then the DFS will never reach U. Okay, so to address this issue within the graph, we simply want to make sure that every vertex is visited, so we can simply use a wrapper procedure of the DFS-ITERATIVE or DFS recursive procedures. So let's just call these procedures DFS upon G. So it's a simple for loop. So for each vertex within that graph, if that vertex is not visited, we will call a DFS recursive using that vertex as a source vertex. Okay, and these two algorithms, they are just equivalent, only except that one is calling the recursive algorithm, but the other one is calling, the second one is calling the iterative algorithm. So this DFS makes sure that all the vertices in the graph are visited. Okay, but the result is not necessarily a tree, but it could be a forest of trees. It will be a collection. So a forest means a collection of different or independent trees, because if you some vertices, some trees, some vertices may not be reachable from some source vertices. Okay, so in the example here, if we start from W, so if we call DFS on G, and we assume that W is called first, is used as a recursive uh, um, W is used as the source vertex first, so it will result in two trees, which together count as a forest. So the first tree has W as the roots, and it goes from W to X, and X to V, right, and X to Y. Okay, and then the second tree could be U. The second tree is U because U is not reachable from W. Okay, so the results of a DFS is very sensitive to the source vertex that you choose. So choosing a different source may result in a very different DFS trees or DFS forests. So in this case, if you choose U, then there will never be a forest. It will be just a one complete DFS tree. Okay. So, all right. So far we have implemented simple versions for DFS, which either go through all the vertices recursively or iteratively, and we can record the parents relationship between these vertices in order to get the DFS tree or DFS forest. Okay, but since DFS is so commonly used, and it will be very useful in analyzing the topological structure of the graph, we need a more sophisticated implementation for DFS, which should preserve more, much richer information other than the parents, other than the whether it's visited or not information, but we also need to record when each vertex is visited and when each vertex is finished. So from the next slide, we'll implement a more sophisticated version for DFS, and using that sophisticated DFS, we can obtain much more information that will be useful about the graph. Okay, so now we will look at this enhanced version of DFS, depth first search. So this procedure will color verticals during the search, and each vertex. So it's quite similar to the BFS procedure, but not exactly the same. So each vertex is initially white, and when it is discovered for the first time, it becomes gray, and when it is finished, it becomes black. So by finished, it means that when all of its adjacent vertices have been examined, or when its adjacent list has been completely examined. So besides, we also have two timestamps for each vertex. The first attribute called D. So the D attribute records the time when a vertex V is first discovered. So it records a time when the vertex become grayed. And note that this D is different from the distance property, the distance attribute in BFS. So this time the D stands for discovered. Okay, so it is the time that a vertex is first discovered. And the second attribute, f. So this f attribute records the time when V's adjacency list is finished, or f records the time when V becomes blackened. Okay, so these D and F are two critical timestamps that the procedure will record. And it's always true that the D, the discovery time, is smaller than the finish time. So for any vertex, it will first need to be discovered, and then it will be finished in a later time. Okay. And therefore, you can infer that a vertex U is white before the D time step, and it is gray between D and F time steps. And after the F time step, it becomes black, and it will keep black afterwards. Okay, and we will need to use a time variable, which is a global variable, and it is shared among all the vertices. Okay, so we'll need to use two procedures together. So the first procedure is called DFS. Okay, so what this DFS procedure does is to first initialize the color for all the vertices to whites, and also make that parents attribute to be none. Okay, and then it sets the global variable time to be 0. Okay, so the initial timestamp is 0. Before we begin, the time is 0. Okay, and then for each vertex in the graph, if it's white, that means if it's not discovered, then we will call a second procedure called DFS visit on that vertex. Okay, so this for loop from line 5 to 7 will conduct the actual DFS. So it's quite similar to the previous to the previous procedures in the previous slides, in which we use a for loop to call DFS-ITERATIVE or DFS-RECURSIVE. Right. So this time we call a different procedure called DFS visit. So in this DFS visit, whenever a vertex U is first visited, we will increment the time by 1. And then we record the time to the D attributes of vertex U. Okay, so we record the time in D, which is the time that this vertex U is first visited. And then we paint the color of the vertex to gray. Okay, because when the vertex is visited, it must be white, because this if condition in line 6 guarantees that unless a vertex is white, we will visit it. Otherwise, we don't visit a vertex. Okay, so after this color is changed and the visiting time, the D time step is recorded, we'll use a for loop from line 4 to 7 to visit all the adjacent vertices of U. So for each vertex within adjacent list of U, we will visit that vertex if it is white. Okay, and also we set the parents of each adjacent vertex to be the current vertex U. Okay, and then we call DFS visit recursively on that adjacent vertex V. Okay, so DFS visit is a bit similar to the DFS recursive procedure. Okay, but it does additional things, like it will increment the time by 1 and record the visit time, and also paint the vertex to different colors, and also record the parents node. Okay, So after the for loop from line 4 to line 7, after all the adjacent vertices of U is examined and visited, we will turn the color of the current vertex to be black. Okay, and a black means that it's been finished. So we will then increment the timestamp by 1 again, and then assign that time to the F timestamp. So the F will record the timestamp that the current vertex U is finished. Okay, so that's how the two procedures, how the enhanced version of procedures code look like. And then from the next slide, we will use a simple example to demonstrate. Okay, so now let's run through a simple example to see how the enhanced version of this DFS procedure runs. So I attached the code for DFS visit here. So this is a recursive procedure that we will run. Okay, so assume that we start from the vertex U. Okay, so since the global variable time is initialized to 0, and because in the first line, line 1, we increment time by 1 and then assign that time to the D property, to the D attributes of U. So we put the D attribute before the slash. Okay, we put it left to the slash. To the right of the slash it's the F attributes. Okay, so we start from vertex U. So U is colored to gray according to line 3, and starting from line 4, we use a for loop to go through all the adjacent vertices of U. It has so U has two adjacent vertices, which is V and X. So we just randomly select, choose that we visit V first. Okay, so because V is currently white according to line 5, the if condition is satisfied, so we will set the parent attribute of V to be U, and then we recursively call the DFS visits on V. Okay, so this recursive call on V will increment the time by 1, so the global variable time becomes 2, and the color of V is also painted to gray. Okay, and within this call, we will examine the adjacent vertices of V, which is just Y. Okay, so we'll need to further call the DFS visits on Y. So the calling on Y will again increment the time by 1, and then the D time, the D attribute of Y is 3, and we need to go through the adjacent vertices of Y as well, which is just X. Okay, so X is next visited. The visiting time, the D time for X is 4, because we need to increment it. Okay, so after V is colored to gray, we need to examine all the adjacent vertices of X. So X has one adjacent vertex, which is V. Okay, but since V is already gray, so the if condition in line 5 is not satisfied. So we will no longer need to call DFS visits on V again. Okay, and that means all the adjacent vertices for X is now examined or finished. So we will need to paint vertex X to black. Okay. And also, before that, what we didn't include in this DFS visits procedure is that we also give all the edges in the graph and label. Okay, and I will just show the statement here. So we call the edge from X to V labeled as back. So use capital B as back because it's pointing from some vertices it's pointing from some vertex X to the to some old vertex that has already been discovered. Okay, so this kind of a backward edge. So in terms of these labels for the edges, we'll have a later slide to explain how the different categories look like. Okay, so we just need to note that we will have such an operation during this DFS visit. Okay, so after X is finished, it's painted to black, and according to line 9, the time will also increment by 1, and that time is assigned to the finish time, the F time of X. Okay, so X is finished at time step 5. So after X is finished, that means all the adjacent vertices of Y is finished as well. So Y will be the next vertex that is finished. Okay, so Y is painted to black as well, and the time is incremented by 1 on top of the 5. So the time will be 5 plus 1 equals 6. So the finish time of Y is 6. So after Y is finished, all the adjacent vertices of V are also examined. So V is the next one to be finished. So the time will increment by 1 from 6 to 7 and assigned to the F attribute of V. Okay, and now since X and V are all finished, are all examined, then that means all the adjacent vertices of U is already finished. So U is also finished by increment the time from 7 to 8 and assigned to the F attribute of U. Okay, so notice here that we also label the edge from U to X as a forward edge. So as I just said it before, we'll explain later to see how different edges are defined. Okay, so at least so far we have seen 3 types of edges. So all the highlighted edges are the edges that form the DFS tree. So U pointed to V, V pointed to Y, Y pointed to X. So these edges are those form the DFS tree, and the other 2 edges from U to X is a so-called forward edge, and B is a so-called backward edge. Okay, so let's just finish the DFS enhanced DFS procedure first. So far, 1 DFS tree is built, okay, and the other 2 vertices W and Z, they are not reachable from the source vertex U, so they will be a second independent tree. All right, so assume that the next call of DFS visits is on vertex W. Okay, so remember that we keep the time a global variable, so that means we'll keep track of the time, the value of time. So now when W is first visited, time will increment from the latest finish time, 8 to 9. Okay, so 9 is 8 plus 1. So the 9 will be the visit time, the D time for W. Okay, and this time we also add another new type of edge, which is from W to Y, and we call it C, and it's for cross because this is between 2 different DFS trees. W doesn't belong to the tree formed by U, V, X, and Y. It's from a second tree to the first tree. So this edge is called cross edge. Okay, and after W is visited, we need to examine from line 4 to 7 to examine all the adjacent vertices of W, including Y and Z. and since y is already visited, it's not white, so y will be so there will be no recursive call of DFS visits on y, but just there's only one one call of DFS visits on z. Okay, the call on z will increment time by 1 and assign the 10 to the as the d time for z. Okay, so because z has a self edge that starts from itself and pointed back to itself, so when we examine the adjacent vertices of z, we should only check z. Okay, and this edge is also labeled as b for back. Okay, so after that check is done, z is finished. Okay, z is finished means that we will paint z black and increment time by 1 from 10 to 11 and assign 11 to the f time of z. Okay, so after z is finished, w is the next one to be finished as well. So the time will increment from 11 to 12 and then be assigned to the f time of w. So far, a second DFS tree is built, and all the vertices in the graph are explored, and the result is a DFS forest that consists of 2 trees, and also all the edges are given different labels. All the bold labels, they are the labels for the trees, and all the other labels in dashed lines, they are given different label, given different tags. So we have a F label for forward, B for backward, and C for cross. And the result tree, if we lift up from the root node, they will be like this. So the first tree roots from U and pointed to V, and V to Y, Y to X, and X has an edge pointed backward to V from a lower level of the tree to an upper level of the tree. And also we have direct forward level. We have a forward edge that pointed from U to X. And in the second tree, we have the root node as the root node is W, and W pointed to Z, and Z has a back edge pointed to itself. And from the second tree to the first tree, there's a cross edge called C. Okay, so that's the results of running the enhanced version of DFS procedure on the example tree. Okay, so basically now we're going to talk about how we define the labels, how we determine the labels for all the edges in the graph. So we basically do this classification of edges based on the results of the DFS. So the results of DFS is a forest of DFS trees. So based on the structure of the DFS trees and DFS forests, we can tell which category or which label each edge should have. So the principle is that given the forest, any edge in the trees are tree edges, so the bold ones. Any edges that form the trees, which means they follow or they conform to the parent relationship. So all the bold edges are called tree edges, and they are defined by the parent relationship. So the parent of X is Y, and the parent of Y is V and U, and V the parent of V is U, and so as for the W and Z, they have a parent relationship. And the back edges, the B edges here, are those edges connecting from some vertex to an ancestor vertex in the tree. Okay, so a V is the ancestor of X, but it is not a direct parent. Okay, and for the special case of the self loop, we also consider them as a back edge. Okay, so the back edges are from some descendants to some ancestors in the tree, but they don't have the direct parent relationship. And the forward edge, the F edges, are those those non-tree edges connecting from a vertex to a descendant vertex in the tree. Okay, so of course X is not a direct children node of U, but it's a descendants node. So that's why U and X, they are not belong to the, they don't, so this edge from U to X, they don't belong to the tree, but it's called a forward edge. Okay, so any other edges other than the tree, the back, the forward edges are classified as cross edges. So W from the edge from W to Y is called defined as cross edges. Okay, so why we mentioned this classification of edges, because it's sometimes useful to track the meanings of those edges. So DFS can be used to determine the interdependencies between softwares or packages. So think of the node, each vertex in the graph is the name of a software or a package. So some packages rely on the other packages. So, and this root package is required by all the children and descendants packages. So these kind of forward and backward edges, they seem to can be used to identify whether there is duplicate dependencies, or there are incompatible dependencies, or if there is a cycles in those cyclic dependencies in the software packages. So this is just a one simple or possible ways of utilizing those edge informations. Okay. So another information that we can gain from the color of the vertex is that when we first explore the edge, say from U to V, we can decide the type of the edge by the color of the V. So when we first explore V from U, if V is white at that time, then it indicates the edge from U to V is a tree edge. And if V is already gray when we first explore V, then it tells us that UV is a back edge. Okay, for example, at a point of X, when we explore the adjacent vertices of X, which is V, and at that time V is already gray, so that means the edge from X to V is a back edge. And the black edge, and when we explore X as one of the adjacent vertices of U, the X is already blackened, so that means the edge from U to X is a forward or cross edge. Okay, so when we examine all the adjacent vertices of W, which includes Y, but Y is already black, and that means the edge from W to Y could be a cross edge. Okay. So that's the classification for edges resulting from the advanced DFS algorithm. Okay, so now let's quickly analyze the running time of DFS. So we'll use the example of the advanced DFS to do the analysis. So we have two procedures, DFS and the helper function DFS-visit, right? So basically, DFS contains an initialization that goes through all the vertices in the graph. Okay, so and also there are two for loops. The first for loop is for initialization, and the second for loop is to check each node, to check each vertex in the graph, and if it's not visited, then we'll call DFS-visit. So the total will take big theta of v times, because it's just the size of the, determined by the total number of vertices in the graph. So when we analyze the DFS visits function, it is a recursive algorithm, but the nature of it is between line 4 to 7. So essentially, the function for this for loop is to check every adjacent vertex, to check each element or each vertex in the adjacency list. Okay, so because the DFS visits is called exactly once for each vertex. Okay, so when the vertex is already visited, the for loops will basically, there will be no further recursive calls. There will be only a recursive call when the vertex is not visited. Okay, so DFS is called exactly once for each vertex. So that helps, that makes things easier, because we know that for each call, line 4 to 7, the for loop will have that many iterations, and that is the size of the adjacent list. Okay, and the total summation of the length of the adjacent list, we already know that it is at the level of the number of edges. Okay, so this total summation of the length of the adjacency list is proportionate to the number of edges, depending on whether it's directed graph or undirected graph. Right? For undirected graph, it's 2 times e. But for directed graph, it's e. So anyway, it's linear to the number of edges. So that's why, in total, the running time for DFS is a combination of this big theta of v and big theta of e, which is big theta of v plus e. So it is no different from the breadth first search BFS, which is also big theta of v and plus e. Okay, and so that's it for the depth first search of graph, and we basically start from 2 simple versions of it, which is a simple recursive DFS and a simple iterative DFS. And for the iterative DFS, we need to use the data structure stack, which is different from the BFS, which we need to use a data structure queue. And next, in the next lecture, we will talk about how DFS will be used in determining into different applications, which is topological sort and the strongly connected components problem. And that's it for today's lecture.